Hello everyone, welcome to lecture number 4 of the third week. And after Bolzano-Weierstrass theorem and exploring monotonicity of subsequences and sequences as well as some of the theorems, we now at the words to include some problems and solutions for these chapters. So in these chapters we have taken some of the problems and I will give you the solutions to make clear your concepts regarding convergence, divergence of a sequences, monotonicity, and some of the theorems which are important. Their applications are important. That's why their analytical proof may not be included in these lectures, right? So the first problem I have chosen for you that determine whether the sequence an, that is 1 plus of n square, is convergent or divergent. If it is convergent, find its limit point or converging point, right? So look at the how we can go through it. We may go through n tends to infinity and so on, but it cannot help you. So you must be tricky and you must use the already learned theorems. So we have learned monotonic convergence theorem, right? So let us firstly check whether this sequence is given is monotone or not. So since 1 by 1 plus n square is a monotonically decreasing sequence, as you can have these terms something like 1 by 2, 1 by 5, 1 by 10, right, 1 by 17, 1 by 26, and so on. So each term, preceding term is greater than that one's the not like this. So I mean, right? So right. So we have something 1 by 2 is much greater than 1 by 5, much greater than this, 1 by 10 is greater than this, and so on, right? So this is a monotonical decreasing sequence. So this is monotonic decreasing sequence. Each term is decreasing by preceding one. And we know that monotonic decreasing bounded below. What will be the bound? Bound is 1 by 2 and going on, right? Below to the greatest lower bound. And what will be not this? This is here. It's going to be where 0 and so on. 0 is not in this term. So for very large, very large n, small n, it will very near to the 0. 1 beta n, so it's very near to the 0. So what will be the greatest lower bound? The greatest lower bound is 0. And we knew that every monotonically decreasing sequence converges to where? Converges to its greatest lower bound infimum, right? So 1 by n square converges to 0. And you can write directly that limit exists and limit equal to 0. One of the most striking theorem is a sandwich theorem. As its name suggests, that means you have something here and then you have something here, right? This is the sandwich. So it says that if this is an and this is cn, and let us these one as bn, and if it is given that it converges to some number, same number L, there is the same limit point L, then this forced to converge at L. That is the theorem, and we had already knew the proof in our first week of the lectures, in which we have seen that using the epsilon by 2 and taking maxima of m1, two natural numbers m1 and m2, we will have this bn as tending to the same limit L. So an, b, and cn are three sequences such that an, each term of an is less than bn, is less than cn for every natural number small n, right? And if limit an and limit cn has the same limit L, here it is, right? Then this forced to bn as having the limit point as L, so that the sequence bn where bn equal to 1 by n plus 1 ka whole square plus n plus 2 ka whole square 1 divided by 2n ka whole square converges to 0. That's we have going to So that one, right? So use the sandwich theorem. Look at the structure of this theorem. So as you can see here, the structure is something we can put this value. So each term is lying between the two terms, n divided by 2n ka whole square as well as n divided by n square, right? And that means why it is, because n square is less than 2n ka whole square. Therefore 1 by n square is greater than 1 by 2n ka whole square, right? And since n is given, so you can put this n above. So that means each term and each term of this lying between these two terms, right? So the each bn lying between these two terms, n by 2n square and n by n square. Now simplify it, it will comes out 1 by 4n. So what we had 1 by 2n whole square is less than bn is less than n by n square. Cancel it out. So this one, not only this one. So this will comes out to be 1 by 4n is less than bn is less than 1 by n, right? 1 by 4n, where it converges to 0. 1 by n converges to 0. And henceforth, without any calculations, by sandwich theorem, we can say that the bn which is given is converges to 0, right? So that means we had proved here that this bn converges to 0. Now another two theorems which are important, and I am not giving the proof, explicit proof for that, because those proofs are not useful to at this stage. The theorem states that we call it Cauchy first theorem and Cauchy second theorem on limits. So first theorem, Cauchy first theorem on limits, says that if limit of a sequence an is L, then the sum of the terms, that means average of those whole terms, n terms, is also having the same limit as L. So let me explore for you. So we have a sequence A1, A2, A3 and AN and so on, right? These are the sequences it given, and it says that if AN, this is n, so if you are taking limit n tends to infinity of n is L, that means the sequence converges to this point L, right? Then you can have this n 1, 2, 3 to nth term and its average of these average terms, and this limit average is also converges to the same limit as it's the sequence converges. So here it is, right? So 1 by n a1 a2 an is going to be having the same limit as L. So use this theorem to prove that a sequence an where an is given as a nth term, right? 1, 2, 3 to n term, an converges to a limit point 1. This is I am going to prove this one. So firstly I have to find out the limiting point of an. So I have to calculate limit of an first. To calculate this limit, use one of the theorem. So what will be the general term of this sequence? So let's say ak, if I want to calculate ak. So this will be 1 divided by 1 n square plus 1 plus of 1 divided by n square plus 2 till k, right? So that means at least ak is less than or equal to n divided by n square plus k. N is much bigger than the k, right? So because it is 1 1 1, so that means how many terms it has? 1 2 3 4 to n. So this is less than or equal to n, right? So that means limit an is equal to limit n tends to infinity and divide each term by n. So 1 plus of 1n, and this will becomes 1. This will become 1. So this limit of this term an is 1. Now by Cauchy theorem, we knew that the limit a1 plus a2 plus an divided by n is equal to 1. That means a1, what will be the a1? n divided by n square plus 1, n divided by n square plus 2. So a1 is this, a2 is this, a3 is this, and an is this, right? And this is the sum of this. So by the Cauchy first theorem, the average of this, right? So that means we have 1 beta n square plus 1 beta n square plus 2, 1 beta n square plus n is also having the limit 1. Now if you have any problem, then calculate, I am looking for this an as what? An as n divided by n square plus 1, right? So an is nothing but an equal to n divided by a square root of n square plus n, n square plus n. So now take this outside of the square root. So n divided by n, 1 plus of 1 beta n. So n cancel out and it will comes out 1 divided by square root of 1 plus n, and limiting of this limit of an is going to be 1 now. So here if you have any confusion in AK, then you can write this an as directly by n square plus n, right? And then limit is quite easy. So take this n outside of the sequence, a square root, and this limiting of an is going to be 1, right? So that's what we have taken. So we have taken n in a tricky way and find out using the Cauchy first theorem. We prove that the sequence, the limit of this whole summation of this is going to be 1. Similarly, look at the problem number 3. It says that 1 beta limit n tends to evaluate the limit 1 beta n 1 plus 2 pi power 1 by 2 plus 3 power 1 by 3 plus n pi power 1 beta n as equal to 1. So I will look for an as n divided by n pi power 1 by n, and if it is happens, then limit n tends to infinity is equal to 1, right? So then by Cauchy first theorem, a1 plus a2 plus an divided by n is going to be 1, right? So the only problem here to find out the limits of them. Do you remember this one, how to find out? You can do it by using there are two methods, but you can use the simplest way. This is going to use n as equal to 1 plus of h and expand it as a binomial, and you will find out that answer will be 1, right? Or otherwise you will use the theorem, I mean the famous theorem, the Cauchy second theorem, as well as the Cauchy logarithmic theorem, and you will find out the answer of n equal to n pi power 1 beta n is going to be 1, right? So using Cauchy first theorem, since limit n has the limit 1, therefore the average or of the n term of that sequence is going to be 1. So here similarly, Cauchy second theorem on limits, the statement says that if all the terms of the sequence un are positive, and if limit of the ratio of the two terms, the terms and the preceding terms un plus 1 divided by un exist, then so does limit un pi power 1 beta n, and the two limits are equal. That means the limit un pi power 1 beta n is nothing but equal to limit n tends to infinity un plus 1 divided by un, provided the later limit exists, this limit exists. So this theorem containing two important things. The first one is you have to find out the ratio between the terms and its preceding terms, right? Firstly find out the ratio, then find out its limit of that ratio, and then you have the leverage to find out limit un pi power 1 beta n, and both limit exist. So you knew, once you know the limit of ratio of un plus 1 to un, then the limit you can calculate limit un pi power 1 beta n as the same limit as it has, right? So here look at this sequence and the problems. The problem says that so that the sequence a n p power 1 by n converge and find their limits where an is given in a complex way. An is equal to n p power n divided by n plus 1, n plus 2, n plus n, right? Here it is. So firstly, my work is to find out limit an plus 1 divided by an first by given an. So put what will be the an plus 1? So in simpler way, in place of n, put n plus 1. So what will be the last term? Now look at in the last term. So n plus 1 plus of n plus 1. So how much it will gives you? 2n plus 2. So I will go through what will be the first term? First term is n plus 1 is equal to n plus 2. So I will start my sequence, I will start the denominator from n plus 2 and where it goes 2n plus 2. That will be the idea, right? So here it is. So an plus 1 is nothing but starting with n plus 2, n plus 3 and where it will go? It will ends 2n plus 2 and n plus 1 by power n plus 1, right? So limit an plus 1 divided by n tends to infinity, that will be n plus 1, n plus 2 till 2n plus 1, n plus 1 to n plus 1, right? And in the denominator we have 2n plus 2 and into n plus n. That is the term from here to here, right? That is the term from here to here. So the limit will become, now simplify those limits, cancel out each terms, cancel out these terms and you will find out how many terms we have left. We have left 4 terms, the 2 in the upper and the 2 in the lower. So 1 plus 1 beta n power n and 1 plus 1 beta n ka square divided by 2 plus 1 beta n 2 plus 2n. Now look at each term and try to find out the limiting value of this term, because we do understand that limit an divided by bn is nothing but in the individual limit an divided by limit bn, where bn is not equal to 0 or limit bn is not equal to 0. That's we understood, right? Similarly, we understood the limit of an into bn is equal to limit of an into limit bn. Use these two terms, right? So use individual one. So I am taking from here the denominator. The first term is going to be 0 here, so it's going to be 2, right? Because this is going to be 0 and the whole sequences converges to 2. Now look at here, this will also going to be 0, therefore the whole sequences converges to 2. So the denominator have 2 into 2, so therefore 4, right? Now in the numerator we have 1 beta n is going to be 0. So this whole term is 1 plus of 0 whole square. So this will going to be 1, right? Now what will be the value of 1 plus of 1 beta n p power n? Now if you remember your 11 or 12 limiting values, n tends to infinity, it is nothing but it is a exponential and it is a unique one where it lies between where to where? 2 to 3. 2 to 3. So its nearing value is 2.73713 and so on, right? So that means the whole limit value of these two terms ratio is going to be e p power 4. Sorry, e by 4, right? So this is nothing but e by 4, right? Hence using the Cauchy's second theorem, and Cauchy's second theorem says that if there is a sequence an, then an p power 1 beta n limit n tends to infinity can be evaluated and it is equal to an plus 1 divided by an. So and it has given how many it is? It is e by 4. So this limiting value is e by 4. So we had proved that this limiting value an 1 by a converges and converges to a finite number, its number is equal to E by 4. That's the proof of this problem. Now look at another theorem. If an be a sequence such that an plus 1 divided by n is the limit L, where this limit is less than 1, then limit an is going to be 0. That is the theorem. What theorem says? Theorem says that if we have n plus 1 by n as a limiting value L, which is lying between, less than 1, modulus of L lying between less than 1, that means L must lying between -1 to 1, right, here. So if L is lying here to here, then in that case limit of an is going to be 0, right. So now I am going to use directly in a problem, so that for any real number x, limit xn divided by factorial n is going to be 0, right. So here what is an? An is given, an is x by power n by factorial n. Now calculate an plus 1 by an, and an plus 1 by an is equal to, so now calculate it, xn plus 1 divided by n plus 1 ka factorial divided by that means the denominator going to be above, factorial n by xn, x by power n, right, and that means x into x by power n factorial n divided by factorial n into n plus 1 into x by power n. X by power n, x by power n cancel out, factorial n cancel out, so this will gives you x divided by n plus 1 here, right. And taking this limit, so taking this limit n tends to infinity, x divided by n plus 1, and n tends to infinity will give you 0, and this means this is less than 1, this is less than 1. So use this theorem for this problem. What it says, that means the limit of an is equal to 0, right. So that means this will give you limit of x by power n factorial n is going to be 0. That's the proof. That's the proof. So these theorems are quite useful to find out the complex problems for convergence, for limit value, and so on. Now look at the problem number 6. So that the sequence Sn, where Sn is given 1 plus of 1 by n by power n, is convergent, and that limit lies between 2 and 3. This is quite easy to do this, right. So we have to prove this one. As I was already earlier telling you that you may have read this limit in 11 or 12 classes, but now I will show the expanded form or theorem of this one. So look at the structure of Sn. Sn is given 1 plus 1 by n by power n. Now using the binomial theorem, I will expand this one. And how I can write this one? The first term, then n into 1 by n the second term, n into n minus 1 by factorial 2 divided by 1 by n square, plus n into n minus 1 dot 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 to 3 to 1 to 1 factorial n into 1 by n by power n. And now rearrange the whole terms in brackets in such a way that brackets become the positive one. So the first term is 1, n into n plus 1 is also 1, the second term is also become 1. Look at in the third term, so 1 by factorial t, so it is 1 n into n minus 1 by n square. You can cancel out n and n divided by this, so it will comes out to be n minus of n minus 1 divided by n. So this is nothing but 1 minus of 1 by n, right. So using the same thing, you will find out that each term containing in a bracket 1 minus 1 by n, and how much the boundedness of 1 by n? 1 by n lying between 0 to 1. So that means it is always a positive number. It is always a positive number. So each bracket here is a positive number, and henceforth Sn is a monotonically increasing sequence, we have shown here. So, and how many is the monotone? So, look at this problem here, 1 plus 1 beta n, and 1 beta n is also lying between 0 to 1, right? Each term lying between 0 to 1, so bound is 0 to 1. So, Sn has the minimum value as a 2 and Sn has the maximum value as 1, 1 by factorial 2, 1 by 3, 1 by factorial 4, right? As each bracket is positive here, each bracket is positive. So, I am just looking for 1 by 3, 1 by 4 and so on, right? And now use the another inequality, as 1 by factorial t is always less than 1 by 2, 1 by factorial 3 is always less than 1 by 2 square and so on, right? We have seen this one. So, 1 by n, 1 by factorial n is always less than 1 by 2 to the power n minus 1. And how much value it has? 1 plus 1 and going to be 1. So, this is the upper bound of this Sn is 3. So, we had proved that Sn lying between 2 and 3. So, Sn is a bounded and monotonically increasing sequence and bounded above as well. Therefore, it is a converging sequence, the least upper bound. And what will be the supremum? This is the supremum, and how many its value is E. And so E has the bound between 2 and 3. So that is the proof of this theorem, and this problem has some merits. So in real analysis, so you must remember this theorem. The problem 7, in which we are going to use the same thing, Sn equal to 1 plus 1 by factorial to 1 by 3 to 1 by factorial n. And now look at the differences between Sn plus 1 minus Sn. It is a monotony increasing sequence, and we had shown right now that it has the bound as 2. So the sequence is bounded, and if the sequence is bounded and monotony increasing, it is also a converging sequence. So thank you so much. This is the end of the subsequences.